More than 4.5 billion years ago, the Milky Way galaxy collided with a nearby dwarf galaxy. This encounter hastened the formation of stars. Our solar system is a part of the Milky Way galaxy. Within the solar system, material circulation had been progressing. The water component from the outer region evaporated to make materials dry. Through this process, particles were zonally distributed depending on their water content. The bipolar flow stopped, and with it material circulation. Some regions around the Sun with high particle density appeared within these regions. Collisions frequently occurred. Small particles gradually grew to become planetesimals. Planetesimals continued colliding with smaller particles and other planetesimals, eventually growing to planets such as the Earth. A number of planets were moving in the same orbit. The early Earth collided with a smaller Mars-sized planet. Debris from this impact eventually came to form our Moon. The Earth-Moon system as we know it today was in place. Countless planetesimals and icy planets bombarded the early dry Earth. Due to the bombarding water-enriched planetesimals, the Earth became enveloped by an ocean atmosphere system. Water vapor in the atmosphere produced rain, forming an ocean. The atmospheric pressure gradually decreased. The carbon dioxide-rich atmosphere transitioned into a CO2 ocean, covering the water. Ocean carbon dioxide also combined with rock components, and was transported to the bottom of the ocean through weathering and erosion. At this time, the ocean was still toxic with a high salinity and an overabundance of metals. It was too toxic to support life. Upwelling mantle displaced the oceanic plates above. Uplift of the plate by mantle convection caused horizontal slippage due to the weight of the plate. This is plate tectonics in action. Weathered sediments neutralized the ultra-acidic ocean. Heavy metals settled out and became fixed as deposits at the mid-ocean ridge. These deposits were transported through plate tectonics into the deep mantle. By 4.2 billion years ago, a pivotal transformation occurred deep within our planet. A liquid iron core formed at its center, and the churning motion from convection generated a powerful magnetic field that enveloped the globe. This geomagnetic field was a life-saving shield, deflecting the constant barrage of high-energy cosmic rays. Without this protection, solar winds would have stripped away our atmosphere and destroyed any organic molecules attempting to form on the surface. With this shield in place, the stage was set. On the early Earth, a thick, hazy atmosphere blocked the sun, so life began not in a sunlit pond, but deep underground. In the caves of a geyser system, natural deposits of uranium ore acted as a nuclear reactor, emitting radiation. This energy broke and reformed chemical bonds, creating a diverse soup of materials, including the fundamental building blocks of life like amino acids and nucleotides. A continuous cycle began. Geothermally heated water carried these new compounds up to the surface. There, the water cooled before flowing back down into the subterranean reactor. This created a powerful chemical gradient, a reductive environment below ground and an oxidizing one on the surface. This constant cycling between opposing states at temperatures below 100 degrees Celsius was perfect for synthesizing and preserving complex biomolecules. On the surface, another critical process was at play. The Moon was much closer to Earth, creating immense tidal forces. Even lakes experienced significant ebbs and flows, establishing powerful wet and dry cycles along their shores. This was a crucial factor for the next step. During wet cycles, molecules moved freely. In dry cycles, the water evaporated, concentrating the chemical soup and forcing simple molecules together. This drove polymerization, linking them into long, complex chains like the first primitive proteins and nucleic acids. Simultaneously, fatty acids in the water self-assembled into hollow spheres. These tiny vesicles began to trap the newly formed polymers, enclosing them within a protective lipid membrane. This was the birth of the protocell, a distinct entity, separate from the outside world. A boundary had been created between non-living chemistry and a new self-contained system. The threshold had been crossed. This was the beginning of life. Evolution walks a perilous tightrope between continuing and ending. Unstable RNA evolved through ionizing radiation into more durable DNA, making it possible to reliably pass information across generations. And the third stage of proto-life was born. This was the beginning of prokaryotic organisms. This development resulted in the appearance of cyanobacteria. Cyanobacteria produced oxygen which crystallized into felsic iron-bearing oxide, reducing the iron content of the ocean. The thick cloud cover prevented sunlight from reaching the surface of the Earth. The Earth underwent a global glaciation event known as the Snowball Earth. This caused another global mass extinction. But once again, some life survived yet another difficult period. Beneath the ice sheet, tiny life was protected by the Earth's massive circulating system. The prokaryotes survived the snowball Earth, evolving into more complex life, such as endosymbiotic systems living together inside cells. They formed mitochondria and chloroplasts, which allowed them to get more energy from oxygen. A nuclear membrane formed, protecting DNA from the oxygen-dense ocean water. DNA strands grew longer, retaining ever more genetic information. Life evolved into more diverse and complex organisms. At long last, the eukaryotes appeared. The stage for our story was set along the African Rift Valley, where volcanic activity spewed magma rich in radioactive elements. This high-energy environment may have accelerated evolutionary change. It was here a new clade of primates, the Old World monkeys, appeared. These adaptable creatures are now considered our distant ancestors, the first in a long line leading to us. Millions of years later, after hominids began walking upright, our species appeared, marking the dawn of the human era. Deep within our DNA, unique genetic regions called human-accelerated regions experienced rapid change. These regions are key to developing uniquely human traits like advanced brain function, setting us on a different evolutionary path. This genetic divergence fueled an unprecedented expansion of the human brain, occurring in 3 distinct stages. This enlarged brain gave us complex language, the ability to think abstractly, to be conscious, to remember the past, and imagine the future. This powerful new mind allowed for sophisticated problem-solving and the birth of culture. Equipped with these new abilities, humans began to explore. The Great Migration of our species began around 70,000 years ago. These descendants of mitochondrial Eve proved incredibly adaptable, crossing deserts and ice bridges. They eventually reached the Americas 15,000 years ago, having spread from Africa to every habitable corner of the globe. For most of our history, humans were nomadic, but around 12,000 years ago, the invention of agriculture and livestock production provided a stable food supply. This allowed communities to settle in one place, leading to a rapid increase in population. With a food surplus, various occupational specializations arose beyond farming. These growing settlements became hubs for trade, forming the first cities, which in time developed into powerful city-states. To maintain order in these dense populations, new social technologies were invented, currencies to standardize economies, and formal systems of laws, courts, and police to govern society. Then, the Industrial Revolution, beginning in Great Britain, applied scientific knowledge to create world-changing technologies. The steam engine powered factories for mass production, shifting society from farm to city. The invention of the steam locomotive further connected the world, enabling rapid, large-scale transportation of goods by railway. The 20th century brought the information revolution, sparked by the invention of the computer. This gave humanity the processing power to tackle immense challenges, including the calculations needed to explore the universe. The revolution culminated with the internet, creating a globally connected network that launched a new era of instant communication and access to information. As humanity moves forward, progress in medical technology and the widespread intake of nutritious meals dramatically extends lifespans. This success, however, leads to explosive population growth, straining our planet's finite resources. Projections suggest that as a result, serious food and water shortages will become critical issues, marking the beginning of a challenging era defined by billions of climate and resource refugees seeking survival. Simultaneously, in the field of science, innovative technologies will be developed at an accelerated pace. To secure humanity's future, we will build a permanent space base on the Moon, a crucial stepping stone for the exploration of our solar system's planets. Advanced, artificially intelligent robots will be indispensable partners in this endeavor, performing dangerous construction and paving the way for human explorers to venture deeper into space. On a geological timescale of millions of years, the Earth will face more upheavals than ever before. Plate tectonics will continue their slow dance, and centering on Asia, all continents will gather to form the supercontinent Amasia. This will create vast, arid deserts in its interior and new mountain ranges. The appearance of the supercontinent Amasia will lead to an increase in the land area that can fix carbon, but the climate will be one of harsh extremes. In about 1 billion years, the sun's increasing luminosity will trigger a runaway greenhouse effect. The oceans will boil away, and our world's water will be lost to space. Finally, all the Earth's life disappears. The heating up of the solar surface increases the Earth's surface temperature to 500 degrees Celsius, and the Earth becomes a sterile, Venus-like planet. In roughly 4.5 billion years, the Andromeda Galaxy collides with our Milky Way galaxy. While direct star collisions will be rare, the gravitational merger will compress vast gas clouds. Because of this collision, the birth rate of stars increases dramatically. With time, many of these massive new stars undergo supernova explosions, and intense galactic cosmic rays rain down on the barren Earth, sterilizing its surface. In 7.5 billion years, the Sun will exhaust its core fuel and swell into a red giant. The expanding Sun will swallow Mercury, Venus, and then the Earth itself. This is the day when the planet Earth that gave birth to life will disappear from the universe. But perhaps our legacy will endure. By that time, the Earth's life may have reached other galaxies, having evolved into self-replicating artificial life in a different form, carrying a spark of consciousness to new worlds.